We'll wait for 2 more minutes for the others to join. Well, maybe let others to join in the meantime. So I will start this. Just a minute. So let me introduce myself. Myself Ganesh Kumar. I'm a research scholar from IIT Madras. So this is the first problem solving session for this advanced thermodynamics and molecular simulation course. So and every week we will be having this problem solving session around 4 to 6, and we will for this day we will start with the assignment questions. Basically this session is for to uh, basically for the difficulties you are facing while so, solving the assignment problems. So in this session, like, we will start with the week 0 questions. Maybe the answers are quite available. If you fill it up, you will be provided with the answers. So let me start with the week 0 questions. So for these week 0 questions, like, you don't need to see any assignment problems. Like, if you have done this advanced thermodynamics in your UG, you are quite able to do quite able to answer any of these questions. So the first question is as follows. Like, it says the unit of fugacity is. Can anyone answer? Like, it's a simple question. Like, you can answer in the chat box, or if you can unmute yourself and you can say the answer, like, it is well appreciated. Okay, then the units of fugacity is nothing but, like, the fugacity is nothing but the real gas pressure. So it will have the units of pascals, and the fugacity have the units of pascals, whereas when it comes to the fugacity coefficient, which is nothing but F by P, so which is dimensionless. And coming to the second question, which where the question is like entropy is zero at. So this question is basically the third law of thermodynamics. If you look into the videos, like the starting videos, like week 1 or week 2, you will quite know what is the third law of thermodynamics. And the options is as follows, which says entropy is zero at 0 degrees Celsius, and solid at all temperatures, and solid at 0 degrees temperature. But if you see, it will be zero only at 0 degree Kelvin, not at the 0 degree Celsius or any other temperature of any solid or liquid, whatever the phase it may be. So the answer is like none of the above. And coming to the third question, like which is a basic, you know, a overview question, I can say. Uh, Following is a type of a molecular simulations. The options is as follows, like computational fluid dynamics, or Monte Carlo, or molecular Brownian dynamics, or molecular dynamics. Maybe you would know the answers are like these three, not the computational fluid dynamics. If you are a chemical engineering student, or any applied mechanics student, like you will know well about the computational fluid dynamics, uh, but which is not a molecular simulation. But these three types of molecular simulation, where Monte Carlo is quite related to quantum mechanics, whereas these two are related to classical mechanics. You will be looking into molecular dynamics and Monte Carlo in after like week 6. And Brownian dynamics is another class of classical molecular simulations, where people will be using Langevin dynamics. So that maybe you will be see in the maybe after week 6 or week 7. So the answer for this question is like these three. It's a multiple option question. And the next question is follows, like following is assumed in ideal gas model, which is basically the assumptions of an ideal gas. Uh, this is also a multiple option question, like uh, one has to select the options which are the assumptions of the ideal gas. So the options are as follows, like one is the particle are spherical, particle do not occupy volume, and particle do not move, or particle do not interact. So basically the assumptions of ideal gas is are as follows. So the particles are of equal size, like it doesn't mean to be they are spherical, they can be any type of shape, so it need not to be a spherical. And the particles do not occupy any volume, yes they have a point volume. uh, and uh, and they will move and they will collide, like the collisions are like elastic collisions. So there won't be any interaction between the particles, like particles won't stay close together, they will just it's like an elastic collisions. So the two options would be like particle do not interact and particle do not occupy any volume. So coming to the final question in the week 0, which is how the enthalpy and internal energy are related. So you maybe you will be well known that H is related to U as follows, like H is equal to U plus B. And this ends the week 0, and I will start with the week 1. These are sample questions which are not the questions there in the actual week 1 assignment. And the first question is as follows, like the energy of an ideal gas system is 10 kilojoules at 100 degrees centigrade. What is its value at 200 degrees centigrade? Maybe up to this point, like as maybe you people have done week 0 question, so I haven't asked you whether what is the option, or what is the right answer would be, like from here onwards, like uh, I ask you to take time and to solve these questions. Maybe it will be somewhat useful to solve your assignment problems. That's what this session is meant for. Here the question is like there is an ideal gas and ideal gas system, and its energy E is equal to E, or whatever notation you use, like it is 10 kilojoules. And the temperature, this is at a temperature of 100 degrees centigrade. And the question is like what is the energy at 200 degrees centigrade? uh, Maybe from now onwards, like I expect answer from you. uh, you can type it in the chat box, or you can unmute yourself, or and try to attempt it. You can take a minute like to solve this question. So you can consider these options as like A, B, C, D. Can any of you guess any of these options? Like, it's fine if it was wrong. Okay, let me solve this. So if you look into the starting videos in the week one, so where you will find the energy is related to nkbt, where n is nothing but number of molecules, where k is Boltzmann's constant and T is temperature. So this is for an ideal gas system, and this is an energy. So see here in this case, like n is constant, and anyway kb Boltzmann's it's a constant. So you can write it as E is directly proportional to T. So which I can write it as E1 by E2 is proportional to T1 by T2. But here the question is like in thermodynamics, don't try to use directly in the degree centigrade, try to convert it into uh, Kelvin scale. This is nothing but 373 Kelvin, and this is 473 Kelvin. So energy E1 by E2 you can directly write, because when you take the ratios, like all other constants will go off and it is directly equal to uh, T1 by T2. So you have a E1 which is 10 kilojoules, and E2 which is T1 is 373, and this is 473. So if you do some mathematical operation, that's E2 will comes around some 12.69. This is the answer for this question. So we'll move on to the second question. So this is maybe quite related to one of the problem in week one. So the probability of picking up a chord between numbers 2 to 4, which is nothing but 2, 3, 4, and which has to be hearts, like in the deck of cards, like we'll have a 52 cards, like in that we'll have four sets, like one is hearts and one is clubs, one is diamonds, and out of four, like it has to be between 2, 3 and 4. What is the probability of getting 2, 3, 4, like in the three random picks from a well shuffled deck? So basically the problem is nothing but we have a deck of 52 cards. So when we are picking one card at first, so we have 52 cards, and the question is like you have to take three cards like one by one from a well shuffled deck. So what is the probability to get these three cards? Has to be 2, 3 and 4, which is of hearts. Maybe I can say Maybe you can take a minute to answer this, and you can consider these options as A, B, C, D. If you got the answer, like you can, oh, 415, which is B. Yes, this is the answer, like as Pritham said. So let me explain like how it is happened. Like when you take the first card, you will have 52 cards, out of which there will be only one heart, one two which is of heart. So first probability would be 1 by 52. Whereas when you are taking the second card, you this card will be removed. So you will have only 51 cards. Just a second. See, maybe the answer you have said is like when you have taken three cards at a time, then whatever the answer you said is correct. But whatever the question I asked is like taking card one by one. In that case, you will be having 52 cards. So it will be you will have overall of three, out of which like you will have 52 cards. From 52 cards, you can take three cards, and in the second while you are taking in the second time, you will have only two cards because one of the card has been already removed from the deck, so you will have 51. And yeah, and it is 50, so which is 3 factorial divided by 52 into 51 into 50. I think I got confused. Yeah, the B is correct. So we'll go to the next question. So the question is like the total number of ways to distribute three quanta among three persons. So in the lectures as well, like where the professor assumed quanta is like chocolates, and the persons is like as persons, like how these three chocolates will be distributed among three persons. So can someone try this? I think I got something got mixed up here. Just a minute. So the question is not proper. Like what it has to be is like in such a way that one guy will get. I mean one. So this is not the persons. This is actually molecule. Two quanta for one molecule. Basically, there are basically levels, molecular level. So basically, there are three quanta. So in such a these three quanta has to be distributed among these three molecular level, whereas one molecular level will get two quanta. So the number of ways, the possible number of ways is like, so you can remember the number of ways. W is equal to n factorial divided by n naught, n1, n2. So I can name it as n0 level, n1 level, n2 level. So when n2 level is getting 2 quanta, so either n1 has to be 1 or n0 has to be 1. So it will be like out of 3 factorial, so 1 factorial multiplied by, because n2 is getting 1 and n1 is also getting 1 and n0 may not be getting. This is basically factorial out of 3 factorial. So this is a 3 factorial base. We'll move into the next question. So a system is having W ways of distribution. Basically the question is like maybe you would have seen in this in the first week lectures. So there is a system and you have molecules. So when the system is distributed into two halves, so before the system is distributed into two halves, the number of ways of distributions is W, and whereas when it got divided into two halves, so this half having W1 distributions and this half has W2 distributions. So how this W is related to these two is the question. Maybe it is quite easy. You can give the answer in the chat box, or it is also fine to unmute and so this question is quite related to entropy, where entropy is related to Boltzmann's constant and log of number of ways of distribution, as S is a function of number of ways of distribution. So the point here is like when you know the relation between the number of ways of distribution, then pretty much you can know the relation between how the entropy is changing when the system becoming half, or if it became double. It's not A, right? So when the system is becoming half and W1 W2 is related to this. Okay. Because basically entropy is related when the system got half. Entropy is basically additive in nature. So S is equal to S1 plus S2. So S1 is related, S1 is given by log W, and S2 is given by KB log W2. So if you do that, S is equal to KB, you can take it as common, and log W1 plus log W2. So log A plus log B is nothing but log AB. So this is related to log W and W2. W and W1, W2 are related by this expression. We'll move on to the next question. So with this, like whatever the sample questions I made uh, were like completed. Maybe if you have any questions or any difficulties in solving these week one questions, especially like we haven't started week two, you can write your difficulties in the chat box, or if you unmute your mic, or if you came up with your question is also fine. Or if that question is maybe quite related to any part of the week one lectures is also fine. Maybe we'll wait for 2 more minutes, and then we'll move on to week two questions, or week two sample questions. We'll go to week two. So one of the topic in the week two is regarding the homogeneous function. So the question is pretty much simple. Like if you have done anything, any if you know about the homogeneous function, that this is nothing. The question is like which of these homogeneous is our homogeneous functions of x and y. So when if a function has to be a homogeneous function, then it has to be like f of lambda x, f of lambda x comma f of lambda y has to be lambda of f of x comma y. So if you substitute like lambda x lambda y in any of the any of the functions, like it has to give like lambda of function of x comma y. Maybe you can try and you can give the answer in the chat box. You can take maybe 1 minute. And this is a multiple option question, so there are multiple solutions within the option. Yes, uh, A and C are correct, because if you substitute lambda over here, some lambda x and lambda y, so here it will be like lambda cube of x square y plus lambda cube y square x. So lambda cube can be taken out. So here you cannot take lambda square out, so it cannot be a homogeneous function. And whereas here you can take lambda square as out of this function, and this is not at all a homogeneous function, because if you kept lambda x and lambda y, so it will be like lambda x to the power lambda y, and you cannot take this power outside, like similar to this form. So the answers is like A and C. We'll move on to the next question. So the equilibrium state of a closed system is given by. So this is the question around 8th or 7th lecture, I guess. Maybe I can give some inputs like equilibrium state of an open system. Equilibrium state of an open system is given by where entropy will be maximum and it keeps on increasing. So what will happen when if it was a closed system? It is a theoretical question. Like if you went through week 2 lectures, like so this is for the isolated system. Sorry, for the isolated system, entropy will be keeps on maximizing. That will give the equilibrium state. So for the closed system, nothing but only energy is transferring and no mass is transferring. So in a closed system, minimizing Helmholtz energy will give the equilibrium state, not Gibbs free energy or the maximizing entropy or the minimizing entropy. So we'll move on to the next question. So the change in internal energy of one component system is given by. So this is for the one component system. You should keep in mind. And what is the expression or the equation which gives the change in internal energy? It's a direct question. Maybe I expect someone to answer in the chat box. Yes. We'll move on to the last question. See, the question is like how a 200 factorial can be approximated. See, if you see a normal calculators, like if you type 74 factorial, it will give some value around some value and then 10 to the power 98 or 99. So when if you go to the 75 factorial, it will give a math error, or it won't able to give like 10 to the power 100. But there are if you type in a normal computers, like I think you can go for 10 to the power 150 or something. But how you can find 200 factorial, like is it how you can approximate it is the question. So this is for to find this, like you can use a Stirling approximation. Where I can give the expression as well, like ln n factorial is equal to n ln n minus n. So you can take 200 as the value, and you can give I expect you to give the approximate value of 200 factorial. Are you able to solve that, or maybe let me simplify it. Uh, ln 200 factorial is equal to 200 ln 200 minus 200. So ln 200 will comes around 5.298 minus 200. So this comes around it comes around 1059.6 minus 200. We can take from here, which is around 8059.6. See, this is equal to ln n factorial, but the question is like how you can approximate the 200 factorial. So the approximation is around n factorial is equal to e to the power 8059.6, which is very quite high. So don't forget to apply exponential to that, because until and unless you apply an exponential form, it won't become a big number. It is a very small number. So this is the approximated value for 200 factorial. So with this, I came to an end for the sample questions of week 1 and week 2, and also the week 0 questions. Like if you have any questions regarding in the week 1 or week 2, or if you find any difficulties in solving the assignment problems, I'm very happy to answer. You can unmute yourself and you can ask your questions, or you can use the chat box as well. Anyway, this is a recorded lecture or the recorded problem solving sessions, and these recordings will be will be provided in a YouTube channel. Maybe I can provide the link to that every week, after the recording, after the sessions, like I will be uploading those videos into the YouTube channel. Maybe if in any case, like if you miss the session, you can look into that in the YouTube channel. Let me reiterate what I have said. So I have discussed regard some sample questions of week 1 and week 2, and I also solved or I have given solutions to week 0 as well, of course, which is also available in NPTEL portal. So from now onwards, like if you have any questions, I'm happy to take those questions. Okay, thank you, Brita. So this is the link to the YouTube channel for the people who joined just now. Maybe you will get the recording of this session in this YouTube channel. If you have any questions, like feel free to ask. Maybe I will wait up to 5:10 or 5:20. If no other questions, like I will end this session.
Bueno, Mara,
For the people like who joined just now, so this is a uh, problem solving session which is meant for assignments. If you find any difficulties in solving your assignment problems, or if you have any doubts regarding that, feel free to ask. For the past 15 minutes, like I have shown some sample questions for week 1 and week 2, and also the solutions to week 0 as well. So you can find this recording of this session in the YouTube channel. Maybe I can reshare it in the chat box. uh, you will get this recording maybe in tomorrow or day after tomorrow.
Hello.
Yeah, yeah,
Good afternoon, sir.
yeah. Good evening.
Sir, can you explain Helmholtz free energy and Gibbs free energy difference?
So, okay. So you're asking the difference between Helmholtz free energy and Gibbs free energy, right? This is
Yes, sir.
basically U plus PV, and this is H minus Ts. So in the weekly lectures, like if you look into the week 2 lectures, like it was started from enthalpy calculations, like U is equal to, what is this, some, so the internal energy is nothing but TdS minus PdV, right? So this is basically, an heat, and this is basically work. So when we do the legendary transformations to this, uh, so when you differentiate this energy, like du by ds, so when internal energy is differentiated with ds at constant v, you will get a temperature, right? So from this, like if you look into the legendary transformation, which is nothing but if you take y-axis and x, so legendary transformation is nothing but a curve will have a slope m and a intercept phi, right? Like and these phi and m, and this can be written as like pi minus 5 divided by x minus 0 is equal to m. From this, like we define phi is equal to y minus mx, right? So this is from the legendary transformation. So here phi is nothing but u, and m is nothing but t, and x is nothing but s. So the phi is equal to uh, y is nothing but u, right? U minus m is ts. So you asked about the difference between the Helmholtz energy and Gibbs free energy, right?
Yes, sir.
So this is enthalpy actually. So F is equal to U minus Ts. Sorry for that. So
Human.
from this it was defined, like using the, so similarly if you so this is for a single slope, but if you add multiple slopes, like this is for the Helmholtz energy, whereas if you try it in the other side, like tau u by tau v at constant s, you will get minus p, right? So you will apply the legendary transformation to this, you will get the other one, which is the enthalpy, like you will get the expression for enthalpy, which is u minus u plus pv. So if you add, this is for a single slope and single uh, uh, what do you call the, y is equal to mx plus c. C is an intercept for a same intercept. But if you have a multiple intercept, like,
Sir,
yeah, tell me. Yeah, go on.
हेलो.
Yeah, finish.
सर यहाँ पे सर हेल्महोल्ट्ज फ्री एनर्जी में ये टेम्परेचर और वॉल्यूम भी कांस्टेंट रहता है ना?
In Helmholtz energy, so you can,
टेम्परेचर एंड वॉल्यूम.
so you
हाँ
just
सर.
differentiate it du. minus d of ts, right? So it is du is nothing but tds minus pdv. So this is dtds minus sdt. So tds will go off, minus pdv minus sdt. So v and t will be the controlling variables. So for Helmholtz energy. Is it did I answer your question, or
Yes, sir.
let me take the new slide?
Last time. Sir, what is free in Gibbs free energy, sir? What is the physical significance of it?
Is it free in the Gibbs free energy?
Yes, sir.
Good question, but I haven't think like that. Maybe I can answer you in the next week.
Okay, sir. Thank you. Sir, I have another question.
Yeah, go on, go on.
Uh, why the heat is called as random motion, whereas work is uniform motion? Can you explain that with some examples?
Why heat is
A random motion and work is uniform motion. I have read somewhere, but I don't know how. The examples can you give me?
so you're saying heat is wait a second.
Yes, sir. In some textbooks, it's mentioned as heat. Heat is a random motion, whereas work is uniform motion.
Maybe I can answer like this. So basically, heat and work both are path functions, right?
Yes, sir.
Whereas you can convert entire heat into, sorry, entire work into heat, whereas work from heat to work it is not possible.
Yes.
Maybe that is the reason why that explains, like you said, random motion or
No, can you give me some examples, sir? So I am not convinced with the way I read.
so. Which book you followed for that? Like,
Atkins, sir. Physical chemistry by Atkins.
so you're saying heat. Let me write. Heat is a random motion, right?
Yes, sir.
Whereas work is.
Uniform.
So basically, there is a explanation that work is a higher form of energy compared to heat,
Okay.
right? Of course, this explains like why I said heat can be converted into work, whereas work entire work can be converted into heat, whereas heat cannot be converted into entirely converted into work. And regarding the explanation to this, maybe if you like see in the week lectures where like the professor came up with a explanation like if you add some heat, like heat is nothing but adding quanta, whereas work is related to of course something which will broadens your energy level, whereas heat, like you will have some additional quanta that will be added to the molecular level, whereas this will keeps constant. I mean, there won't be any change if you add heat into the system. Whereas if you add work, like these energy levels will broaden, or based on the heat is going into the system or out of the system, it will vary. So maybe I can say like the random motion is nothing but, so there is a distribution of these quanta between the energy levels, and is maybe the uniform motion like you are talking about, it is due to the uh, the broadening or stiffening of these energy levels. Hello, I think you left.
So just a minute. Half an hour.
there any other questions, or I will end this session with this? If you have any problem in unmuting yourself, like you can type your question in the chat box as well. So if no other questions, like I will end this session here. Thanks for joining.